Remember that the difference between the short and the long run is that in the long run, you can vary all of the inputs. So let's assume here then that your fixed cost is going to be zero. Since all of your inputs could be varied, you could pick the optimal size of uh, any input that you use. So you don't actually have any fixed costs in the long run. So in reality, some of these costs are going to be avoidable costs, like rent. You could just stop renting a space. But for simplicity here, just to make our lives a little easier, let's assume that in the long run, there's no fixed cost. You only have variable costs. So your cost is just going to be your variable cost. Now, in the long run, your cost is never going to be higher to produce Q units than in the short run. Why? Well, it's simply because anything you could do in the short run, you could do in the long run. But the converse is not true. In the long run, you could pick the optimal level of capital, but in the short run, you're stuck with some level of capital. You can only optimize the level of labor that you use. So whatever you would do in the short run, you can do in the long run. But in the long run, you have more flexibility in terms of the fixed input, or rather the input that would be fixed in the short run. Now we need to figure out in the long run which bundle of inputs you're going to use. So we're going to use here the concept of the isoquant that we've seen previously. Remember, an isoquant is a curve that runs through all the combinations of inputs that give you the same quantity of output. So an isocost line, on the other hand, is a line that runs through all the pairs of inputs that cost exactly the same amount. That's somewhat like a budget line. So given a wage rate W and a rental rate R, so this is the price of labor, this is the price of capital, all pairs of inputs, L and K, so remember, we're just assuming here that the two inputs that you have are labor and capital. So what are all the pairs of labor and capital that cost exactly C bar for some fixed constant C bar? Well, it's any bundle L and K such that W times L plus R times K exactly equals C bar. So this equation gives us all the bundles LK that cost the same, which cost C bar. So if you were to plot this, if you wanted to plot this, we would solve, if we are going to put capital on the vertical axis and labor on the horizontal axis, we'd want to solve for capital in terms of labor. So then we would get C bar minus WL divided by R. In other words, C bar over R minus W divided by R times L. So that's going to give you a straight line of slope minus W over R. This should be very familiar. If you go back to the expenditure minimization exercise that we saw for the consumer, remember we were looking at these bundles of goods that cost the same amount. Well, they would all define these straight lines of slope minus P1 over P2. Here, good 1 is input 1, good 2 is input 2, or labor and capital respectively. So we're just relabeling things. Instead of P1, we have the wage rate. Instead of P2, we have the rental rate. So the price of the first input, which is labor, price of the second input, which is capital. So again, like I said, we've got these straight lines of slope minus W over R. The vertical intercept is going to be C bar over R, and the horizontal intercept is going to be C bar over W. So they look kind of like this. Let's suppose we had some wage rate of 5 and rental rate of 8. Then we would have the straight lines of slope minus 5/8. The vertical intercepts would be given by C bar over R. So when C bar is 100, so again, these correspond to all those bundles of inputs that cost exactly $100. Well, if you're using all the $100 to buy only capital, capital costs $8 per unit, well, you could buy 12.5 units of capital. Or you could spend all your $100 on labor, and you could, since it costs $5 a unit for labor, you could buy 20 units of labor. Similarly, for C bar equals 64 and C bar equals 40, we would get these straight lines of slope minus 5/8 and the corresponding intercepts. Of course, the higher the line, the higher the cost. These bundles of inputs all cost 100, whereas these all cost 40. So the higher you go, the more expensive the bundle of inputs. Now, the goal here, if we want to find the cost function, is to find the cheapest way to produce Q units of output. Right? So we want to find, given a level of output, what is the cheapest way to produce that? Well, there's 3 ways to do that. These are going to correspond to the ways we found the optimal bundle for the consumer. Well, the first is the lowest Isocost rule. So look at the Isoquant for that given level of output and pick the point on that Isoquant that is on the lowest Isocost line. The next way to do it is the tangency rule. Pick a point on that Isoquant that gives you that level of output where the Isoquant is tangent to the Isocost line. And the third way is what we call the last dollar rule. So the last dollar spent on any of the inputs, so there's 2 inputs, labor and capital, the last dollar you spend on labor should give you the same additional output as the last dollar you spend on capital. So whether you spend it on labor or capital, the last dollar should give you the same level of output. We'll look at these 3 in a little more detail. They're all equivalent. And of course, let's keep in mind, these are all when you get interior solutions. You should always be careful when you use these methods because these are for interior, these are assuming that you have an interior solution. You may have a corner solution, in which case you have to use some common sense. So let's look at that lowest Isocost rule. So in the figure we've got here, we want to produce Q bar units of output. So we draw the Isoquant where we've got Q bar units of output. So we want to find the cheapest way to produce Q bar units of output. Well, of course, Y is one way to produce Q bar units of output, so is X. But the bundle Y is on a higher Isocost line than X. So Y is a more expensive way to produce Q bar than X is. In fact, X is on the lowest Isocost line of all of these bundles that give you Q bar units of output. So if everything is nice and you have an interior solution, then this lowest Isocost rule is exactly equivalent to your familiar tangency condition that just erase this to make things a little clearer. What we're looking for here is that at the point X, we've got tangency of the Isocost line and the Isoquant. Which brings us to the tangency rule. If you recall, the marginal rate of technical substitution is the slope of the Isoquant. At tangency, we want that to equal the slope of the Isocost line, which is, as we saw, minus W over R. So it's a negative ratio of the prices of the inputs. So if we set those equal to one another, we've got, remember the marginal rate of technical substitution is just the negative ratio of the marginal products. So the negative signs cancel out, and then we get the marginal product of labor divided by marginal product of capital has to equal the wage rate, or the price of labor, divided by the rental rate, which is the price of capital. If we rearrange this, we get the equation marginal product of labor divided by wage rate has to equal marginal product of capital divided by rental rate. In other words, if we look at the marginal product of each input and divide it by the price of that input, and that has to be equal across all of the inputs. We've seen this before. Instead of marginal product, we had marginal utility, and we had the price of the goods when we were looking at the consumer. And so that's just the bang for your buck. So it's the extra output you get. So what is this? If we look at the marginal product, so let's look at labor. The marginal product is extra unit per hour of labor. Wage rate is dollars per hour of labor. So what's on the left here is the units you get per extra dollar spent on labor. Similarly, on the right side, we've got units per unit of capital. And this is the rental rate is the cost of a unit of capital. Of course, this is just units per dollar. So for every dollar that you spend additionally on capital, how many more units do you get? That's what the right-hand side tells us. What this equation says is that, well, if you look at that across the two inputs, it has to be equal. So the bang for your buck, so the extra units of output that you get per dollar spent on labor has to equal the bang for your buck, or the extra units you get per dollar spent on capital. And that's what the tangency rule tells us. Or this is nothing but the last dollar rule. So the tangency rule is equivalent to the last dollar rule. So all three of the ways of solving this problem when you have an interior solution are equivalent, just like they were when we were solving the consumer's problem.